Hello everyone, and welcome to I think it's the fifth stream of the Flying Fox. Today we will be exploring a few topics, especially re-explaining Verlet integration and going more in depth in why we use more classes than structs in C#. Because last time the explanation wasn't that good, I'll admit it. So, let's start with the explanation. Let's start with showing the checklist for today. So, as you can see, we will explain the classes and structs more. We will add acceleration and mass to our game, and we will polish and refactor some of the old code. Let's get right into it. So, I made a little note for us. If you look in the code of the Flying Fox, you will see that there is a sprite system, a rigid body system, and sprite and rigid body components. The registry is where everything is stored. So you can, this is like just an array of all the components. So it's easier to get to the components and everything. The idea of a struct is faster access. The problem is that when you use, let me just use better words. Problem is when you use structs, they are not passed by value and not passed by reference. So if you look here, we have a player position, and a player position. All of these need to refer to the same player position stored in the registry. Otherwise, you're going to have to call update on each of them. Now, in C or C++, whichever you prefer, you can store a vector 2 in the registry. You can pass a pointer to this player position to other methods and, structs. So a sprite struct or a rigid body struct. This will be done like this if you use a pointer to a vector, a pointer to a pointer vector. Then you can just update that reference and the original vector will be modified. Otherwise, if you don't use a pointer, you're just creating copies and you're not actually changing the values of the original vector. Now, let's look at C#. When we store it in the registry, we store the actual player position we want to access. Now, we pass this to sprite. Let's say we're using structs. So just pretend this is a struct. So we pass this struct to sprite and to rigid body. Now, since structs are passed by value and not passed by reference in C#, we are creating copies of the structs. So to make this more visual and show a little map of how it works, we have the registry here, the rigid body component and the sprite component. Here we create, at the start of our game, we create a player position and we initialize the player position in the rigid body and sprite class to this value. However, this is a pass by pass by value and not a pass by reference. So this means we are creating new instances of player. So this is not equal to the actual original value. Now, if we want to move our player, we call update to update this one. However, these remain exactly the same. You will see that nothing changes. Your player will just stand there and nothing will happen. So, as you can see, nothing and nothing here. When we update the Y position with 50 pixels. Now, a possible solution you can think of is by using a reference, storing a reference to the player position. The problem is with this is you have to change your language version and you will get an error because we're using Monogame, and Monogame targets a specific runtime that does not support reference variables yet. Let me show you. Otherwise, this is hard to visualize. Let's just go window. Here we are in our NVS Code with our project. So let's go into Sprite. As we discussed, the solution for this will be to say there should be a reference variable. There we go, first error. Now you can see ref views are not available in C# 10. Okay, so let's change to 11. So we go into our project folder, we go into, we say, lang version, just close the markup, lang version, and we say we want to use C# 11. Okay, so this error will now disappear, as you can see, and there you get it. The next error, target runtime doesn't support ref fields. Now, there is probably a way around this by changing the runtime, but for the simplicity of this series, I'm not going to do that. We are just going to use a simple class. So we have it here, the position class. It stores references to the actual, values. So classes are passed by a reference in C#. So when we pass this position to both sprite and to rigid body, we are storing references to the original position. So then we can just say like position.x plus 10, and it will be updated in the registry, in the rigid body, and in the sprite. So we will see the result of that everywhere. Now of course, you can just, if you'd like to use more structs, we can make rigid body a struct if no other class is going to use it. Because, or at least when you use it from the registry's perspective, you can create a new variable. Let me just show you. So we go into our systems folder, player system. So here we can say if this is a struct. I'm just going to take this out and demonstrate how you can make a rigid body a struct. So this could probably going to be a problem here. Player system. Now here, to still update it, we can just say ref. I think yeah. What's the error? By reference. The reference. Struct. You can just struct. There's a bit of an issue. I messed this up. You see, I'm a bit rusty here. I'm just quickly going to check what I did last time. So, I'm just checking the example I have here. Program. Because we're not going to do it really this way, so it doesn't really matter. There you go. So now we have an actual, the registry is giving us back a reference to rigid body. Now you can just update it. It will work as normal. But since position is not going to work the same way, since it has to be shared between components, sprite and rigid body, and we don't want to call the registry for each of this every single frame, we're just going to store it as a class position. So there we go. That's our first thing. So we can just say that's done. If you have any feedback on this, you can leave a comment and we can discuss it. Maybe you have a better idea than this. So next up on our checklist, let's see here. We want to add acceleration and mass. So to do this, it's easy because previously we put in the force and we discussed, because we're not going to put in mass, or at that stage we won't be putting in mass, the resultant force is just equal to acceleration according to F equals ma. So we can just add actual mass here. Let's go to the player system, or rigid body, sorry, and add a new variable, and this will be mass. Let's say this is 10, this will be can say it's kilograms, doesn't really have units. The actual SR units are kilograms, so you can pretend it's kilograms. So now we want to modify force and acceleration according to F net equals ma. Therefore, we can say acceleration is equal to force divided by mass. Problem is we don't have acceleration yet, so we just create it, put it in here next to velocity, acceleration. And remember to update this part. Now we have mass, so that we can run this code. And it falls quickly. Just going to close this and create us a debugging, allow debugging in this code. I'm creating this folder, this file. Now we can go back. Okay, next problem. We are updating this by refresh rate. That is incorrect. And that is because the formula for Verlet integration is a bit different. Let me just get out my system here and show you again. So wait a minute. So we want just setting up the string. And share my screen. Continue. Start now. Okay. Back to notes. Okay. Let me just hit. Now you admit yourself in this meeting, so it's going to take a while. Okay. There we go. And we will be in Notepad. Okay. So let me explain why we do things the way we do. So first off, the reason we use Verlet integration is because we don't have continuous time steps, because computers can't go and divide, like, let's say there are 60 seconds in a minute and there are like, what's it, 100, I think it's 1,000 milliseconds in a second, and so on and so forth. Now a computer can't run every single second, like every single division of a second. For example, it can't run like 10,000, 1,000 picoseconds and then 1,000. There's not enough divisions. So if we take like a graph, this is a bit more calculus, we want to find the area under this graph. This is a velocity versus time. Just velocity versus time. Why? Because x, the displacement, is the derivative of the velocity and time. So we want to get the area. In other words, we want to integrate velocity to get x, because what is the opposite of derivative? Integration. Wait, I'm wrong order. It is velocity is the integral, not the integral, the derivative of position or displacement. So then you say that x is the integral of velocity and time. This corresponds to the area under this graph. Now, our problem is we can't take this continuous thing. We have to discretize it, because we can't say limit of n to infinity of a summation. I think it's I to n. So if you take a Riemann sum, we can't take the limit to infinity on a computer. Just doesn't work that way. Therefore, we will discretize, and we will draw the graph. I think discretize is the right word. Correct me if I'm wrong. So we'll take velocity again and time. So this is how it will look on a computer. Now we're taking this little part, this little part, this little part. If you've done a little bit of calculus, you'll know this is the Riemann sum. This is where integration methods come in. We want more and more accurate methods to use for this. And a useful thing to know is the Taylor series, because this is where most of the integration methods in games come from. So with other words, we know this function, let's say this is displacement function, is equal to the first derivative, its first derivative. So this is like velocity. Let me just make sure I'm not making a mistake here, otherwise I'm marking it up a bit, because it needs to be precise. So we know that where is it? Where's my reference? Sorry for the inconvenience. So now I should have had this close by. At least I'm on my computer so I can get it quickly. So we know that f of x is equal to f at a plus f, the derivative of f, at x minus a. This is the Maclaurin series, because we're not using, because a is not equal to 0. Then f, second derivative over this. And if we just use a equals 0, this is to infinity by the way, this becomes 3, 4, 5. So we can say that fx is equal to f at 0, if a is equal to 0, f at 0, x plus f 0 to x squared plus to infinity. Now, using this, we can kind of derive Verlet integration. I'm not going to show you the entire process, because I'm not a mathematician, and this is not really the idea of this live stream. We're more concerned about the application. But I'll show you one of the methods used to integrate velocity, like acceleration, into displacement, and this is the Verlet integration. So Verlet, specifically, we're looking at the Störmer, or however you pronounce this, Verlet. We'll just put that in brackets. And what does this formula say? Well, if you look it up on Wikipedia, you'll see that x plus 1, n plus 1, is equal to 2xn minus xn minus 1 plus an times delta t squared. Now this doesn't make sense completely if you just take a look at it and don't really inspect it. because we are taught in school that x is equal to velocity times delta t plus a half a delta t squared. So this is not, you can see obviously this is not equal to each other. But we're using discretization, we don't have infinite time intervals. So you'll see, notice this, n plus 1. This is the next position. So for the position for the next frame, this is the position of the current frame, and this is the position of the previous frame. And this is the acceleration of the current frame. So let me show you a little bit how they derive this. So first, we can say, just look at my notes here. We can say we have x, the time plus delta t. So the position for the next interval is equal to, you can look this up on Arcane Algorithm Archive, I think. I have it in the description. Is equal to this interval's displacement plus the velocity of this interval and a change in time plus a half a t delta t squared. There we go. You see, this is similar, very close to each other. And you can obviously go and say plus of 6b t delta t third power with o delta t of error. This is just the error one, and let's just mark it error. This interesting one is called the jerk term. So this is the derivative of, I think, acceleration, if I'm not mistaken. So you can say, I think this is equal to that jerk term. We will not be implementing this term. Now, if we can take a little trick up our sleeves and say we also know the position, the displacement of the previous frame. So this is equal to this frame minus velocity of the previous frame, or still the current frame. So half acceleration delta t squared minus the jerk term et delta t to the third power. Okay. Oh, don't forget the error. Delta 4. There we go. So since we're not going to use jerk term, we're just going to remove it. So we're just going to like say. Now anyway, if you do what we're going to do next, you can basically ignore this. We will just assume this is equal to 0. But I mean, just wait and see. Let's make this equation 1, and this equation 2. Now, if we add these two, we get the following: x for the next one plus x of the previous one, the previous frame and the next frame, is equal to 2 times the displacement of the current frame. Notice this little minus and this velocity. Look, it will cancel out. So we can not entirely ignore velocity. So we can say plus 0, just as a placeholder for that one. And because we have a half here and a half here, and it's the same term, this is just a or b, whatever you'd like to call it, we can say a t delta t squared. And there we have it. We have almost derived, sorry. We just need this one last step, and this is to solve for this term, the next frame's term. So this one. There we go. Okay. So solving for that, pretty easy. You can solve it yourself if you'd like. you just follow along. There you go, plus a t delta t squared. Here we have it. We have derived Verlet integration algorithm. We may say that this is not exactly the same as what we have up here. You'd be almost correct. I mean, this just means the next frame, and this means the previous frame, and this means the current frame. So we can just rewrite this as x n plus 1 to x n minus x n minus 1 a t delta t squared plus. We have just derived that. If you look in the code we currently have, put that on our screen, go to the rigid body class, you can see we say velocity is equal to transform the new position, or the current position, minus the old position. And this is entirely correct, because we know that velocity is the derivative of x over the derivative of time, or if we have constant stuff, it's this, and this is meters per second. So calling x n minus x n minus 1 velocity is not equal to velocity. It has almost the same effect. For clarity, we'll just rename this field. We'll call it displacement. Position displacement is the same, kind of. But if we have like a delta time of 1, we can also call it velocity. So we'll just keep it as velocity, because we're going to try to make this delta time constant. This is because if you don't keep it constant, Verlet integration will, there's some energy loss. So if you use, let me just show you. If you say the kinetic energy is equal to this, and you want to calculate that, when you don't have constant time steps, the Verlet integration won't work as well, and this won't be conserved, if I can say so. So we'll put that in later. I think also the next video with the magnets and Monogame, you'll also see that it is, what do you call it? It is about creating a constant time step and fixing your time step. There's another article you can read called Fix Your Time Step. Someone wrote it also in Monogame, so you can read the C++ one, I think it's C++, and the Monogame one, C# one. But I mean, that's like, oh, it's not even on our list. We'll just add that. Explain Verlet integration. And we'll just mark that one complete. Yeah. Because we just did that. I mean, we have already finished quite a few things, and it's only been half an hour. Can you believe it? Okay. Why doesn't this thing want to mark? There we go, mark is complete. Now we can go back to our code. Here's our problem. We are multiplying by refresh rate. As I explained, this is a mistake. Remove it. If you look into our formula, it is wrong. You'll also probably want to say, this is, why do we do it like this? Let me show you again. Let's go back to our meeting. So if we say velocity is equal to the current position minus the old position, I think it's this. Let me just make sure I have it correct. Yeah. If we say that and we make the old position equal to the new position, we say in the next part xn plus 1 is equal to velocity plus xn plus an delta t squared, then you'll see if you put in all of the, what do you call it? is you substitute the values. So you substitute it into here. You'll say xn minus xn minus 1 plus xn plus an delta t squared. And what we have, you have the Störmer-Verlet algorithm we derived previously. Delta t squared. There you have it. So we can do just it this way. If you use this, you'll see it also works. Now, because we removed the frame rate, it's going to act a little bit weird. For the sake of this video, and I mean, bear me if you'd like, we're just going to take that delta time away, because it's going to be less than 1. The next stream, we'll make a constant. It's either going to be a stream or a video, but we're going to make the delta time 1. So just assume we did that already, and we're just going to put in nothing there, because I mean 1 squared is equal to 1. It's just me on this one, because otherwise everything is going to update so slowly. But don't worry about that. Maybe we'll do it this stream. Let's test our code. Start debugging. Let's see how. Oh, everything is gone. What happened? So if probably, yeah. Let's see. What did we do wrong? Position or position transform. Velocity. Yes, that's correct. What is our mass? It's 10. Force divided by mass. Acceleration. Yes. Acceleration. We probably need to initialize that. Acceleration is equal to 0.2. Yes. Let's just check again. Yes. Well, it goes very quickly. Player falls so quickly you can barely see. Let's just make this like smaller. And it's still going through. If you notice, from the last stream we didn't fix this. However, I did inspect the code beforehand, and I saw a little mistake. You see the virtual height is 180 and 320. And the map height is 400. And since we're scaling this up, we aren't actually seeing 400. We are just seeing 180. So we can do one of two things. We can change the virtual width and virtual height, or the map width and map height. We're just going to change this one, or actually you have to change both. Or you're just going to have to make the virtual height and width much larger. We're just going to double this and make the map height and map width equal to these. So if we run it now, we will see where the map ends. And as you can see, there's our little guy. And at least not much is happening with him. At least we can see him now. Let's go down a little bit. Yeah, this is fine. This is supposed to be virtual width and virtual height. I'm just making sure. Always make sure about your code before you assume it's correct. Yeah, okay, that's fine. Back to player system. This is gravity currently. And oh, here's another problem. The rb.max.y might not always be equal to the actual map height, so we can just say when it's greater than as well. That's for clarity, if you want to like check it. And then we have constraints here. This is supposed to prevent the player from falling below the map height, so falling off the screen. Let's run the code. There's our little player. It's ever so slightly moving. Probably a bit of problems here. Let's say force times mass, acceleration, transform. Okay, just part out. Force. Let's make mass 1. Maybe that is causing the quick falling or slow falling. Why is it falling so quickly? It's supposed to be falling slower. Let's try this again. Oh, I forgot to change this back to classes. Maybe because it's a struct, it's like updating much faster. Imagine that your computer running faster being a bug. Okay. Another issue I noticed with the previous video is we have this little blurring. And you can see the player's blurring here. Maybe you can see it. I don't know how bad the YouTube compression is, but I can see it. And if you download the code, you will see it as well. This is because you can't have pixels between pixels. There's a set amount of pixels on the screen. So if you're updating something and you add like 0.1 and it's less than a pixel, it will try to range it between pixels. So to fix that, we can just use integer positions on the sprite class. We don't want this to be integers, otherwise we're going to use a lot of data. We're just going to convert this position to an integer. So we'll just convert it to a rectangle. Transform.x and position position.y. We don't even have to we don't need transform here, as we said this previously. And we just have to specify width and height. And something's wrong here. What's the problem? It's a float. There you go. Convert both to ints. What's your problem now? Yes. So if you remove this one, there you go. Maybe you can actually. What is this? No. Sorry. Guess my curiosity getting hold of me. Now let's see here. There you go. Look at that other guy. No blurring. Updating 1 pixel at a time. Another problem will arise now. As you can see, his feet are gone. You can't see his little feet. This is because his width is incorrect. So, the rigid body. No, sorry, player system. You see, I hard-coded the values here. Don't do that. It's supposed to be 14. Because the player is from 0 to 13. So 13 is 13 numbers. Plus 0 is 14 numbers. If you count 0 as well. Let's run this again. Okay, it's falling very slowly, but floaty. Aha. I think it's maybe still incorrect. No, it's correct. Let's see again. I think it's correct. Yeah, it's correct. Okay. Let's just make this bigger because this is gonna take forever if we have to debug it and wait forever for him to actually hit ground. There we go. It falls very quickly. But now, next problem. You can see this guy is not actually jumping. Why is that? Let's see why. Let's debug this. And a little thing here. Breakpoint, start debugging. Now, when you need space, this is activated. Okay, adding a force. Yes. Step into the code. Duration. 90, because it's just equal to the false, because the false is currently 1. You can just say acceleration is 1. Aha. Next problem. Plus. Don't just say equal to. Okay, let's just remove this breakpoint and continue again. Ah, the guy's flying forever. Look at him. Whee. Okay. That's another problem we can fix easily. Is we're adding 90. So we can just make that a little smaller, -9 for example. And here he goes again. Why isn't this picking up? Come on. Is it not big enough? Is that a problem now? Let's see what's the problem. Is this ever even happening? Yeah, it is happening. Go into the code. Go to the next step. The force is -9. It's going to stay in -9. Ah, why? Acceleration is 903. Let's just get acceleration. Should be equal to 0. We should actually remove resultant force entirely. There's another bug. Welcome to bug world. Let's go down. Try this again. There you go, your false. This is invoked. Move the breakpoint to see if it works. Yeah, there we go. Our little guy is moving. Haha. So that's the next part is done. Let's see. On our list, what's our next goal? Just implementing polishing. Oh, this is done. Polishing and refactoring of old code. I think we refactored pretty nicely. Now we can I thought we were gonna take a little bit longer to do all of this, so we're just gonna like add other stuff. So let's add movement. I mean left to right movement. So we can just check if player presses A or D and move them respectively. So was key pressed keys.A. Let's add this just to be fancy. Or input dot was key pressed. And this is keys dot, I think it's right. The right arrow? Yeah. No, this is supposed to be the left arrow. Left. So if the player wants to move left, that side, we remove or we add a negative x force. So apply force. Vector 2. Let's say like -10, 0. Waiting for this thing to go. Okay, something is not working. Why is this not working? Key pressed. Yes, that's correct. Is this even firing an event? Let's see. Why is it not detecting us? Our input was key pressed. Is it left? Hey. What's happening here? Nothing's happening. That's interesting. Why is this never fired? If input yes, was key pressed. I have to debug again. Oh, was key pressed. You want if it is being pressed. So we can just say keyboard. I mean, let's just put this in the input class. to our input class. We implemented it last time or the previous time. Why is there nothing here? What's going on? Let's see. Go to definition. Oh, we implemented this component and it's incorrect. Okay, just delete it. Let's just see if it breaks anything. This is refactoring in a nutshell. Okay, works. Back to the actual input class. It's down, yeah, we got this. This is a terrible method. You can't read it. Let's just say is key pressed. Where is that? Play system, sorry. Input.is. Hey, what's wrong with this? Oh, not static. Is key pressed. It's .a. I'm not going to worry about left right now. We're just going to test A. If it works for A, we can change it for left. There we go. The man walks extremely quickly. It's faster than Usain Bolt. Just key pressed. Yes, key pressed. Yes. Why? No, why? There we go. Run this again. And left. Now let's put in the right. So we can just that, move this that way, and say D and right. Whoops. Okay. Before this thing runs, there is another mistake. Don't make a negative. It has to be positive, so it can move right. Hey. I mean, just look at that. Whoosh. This guy is so fast, you can't even believe it. Oh, we actually need to test like jumping, sorry. Let's make this a little bit smaller. Yes, this updates for every single frame that the key is pressed. We also want to limit like his velocity, because currently we can make him go so quickly that you can't even see him. So let's limit his velocity. To limit his velocity, we're going to take the max and the min. Sorry? We're going to take the min, because if we take the max, it's going to be exactly the same thing. So we're just going to go and go into our rigid body. Or we can maybe we can limit it outside the body in the actual system. We just check our code. Okay, this is fine. Time blah blah blah. Acceleration. Yes. Maybe next live stream we're going to put in velocity display. This is a bit isn't the best, you know. So is this velocity public? I think it's public. Yeah, it's public. Then we can limit it outside. So we can limit the actual velocity of the player here. Maybe that's not a good idea. Add a force will change the acceleration. We want to limit the velocity. Let's check. Let's check this first if it's going to work. Velocity is equal to math. What's system math? Think math helper. What min? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32 33 34 35 36 37 38 39 40 41 42 43 44 45 46 47 48 49 50 51 52 53 54 55 56 57 58 59 60 61 62 63 64 65 66 67 68 69 70 71 72 73 74 75 76 77 78 79 80 81 82 83 84 85 86 87 88 89 90 91 92 93 94 95 96 97 98 99 100 101 102 103 104 105 106 107 108 109 110 111 112 113 114 115 116 117 118 119 120 121 122 123 124 125 126 127 128 129 130 131 132 133 134 135 136 137 138 139 140 141 142 143 144 145 146 147 148 149 150 151 152 153 154 155 156 157 158 limit to 10. Now we want to limit x when the keys are pressed. Check it again. This is just going to work for the left side. We're just going to move our guy. No, it's not working. Let's make this, let's make this 1, just for the sake of testing. No, it's still moving extremely quickly, because the velocity is not actually being limited. Here's a new problem for you. A new bug that we only might fix in the next stream, depending on how much time I have, or if I'm just too stupid to notice how to fix it this time. I mean, that's also a strong possibility. We could say if the velocity is a certain threshold, not to add anything more. We can say group these two actual inputs and say if velocity of x is smaller than, wait, this is not going to be, it's going to be math helper, not apps. This is not have an apps. It's always going to be, yeah, it's going to be negative. So if it should be greater than 10. Otherwise, nothing should happen. Okay, let's try this. Greater than minus 10, guys. Because left is minus with monogame. If we draw our coordinate plane, let's see. Yeah, limited it. Not going faster than that. I think we still have our meeting, except if we kicked us out. Okay. So, let me just show what we just did. Here's monogame's default thing. This is 0, 0. Oh, we're just going to call it big O over here. So usually we have a cost diagram, and we have positive y, positive x, like this. This is the math standard, but in monogame, I think I explained this once, but we're going to explain it again. Monogame does not use that. It uses y is positive here, x is positive here. And not, as you can see, this is other side. Therefore, if we want to move to the left, it's still negative, negative x. But if we want to move to the right, it's positive x. But if we want to move down, negative and positive. So since we're checking first if this player is moving that side, if its velocity is greater than minus 10, this minus 10 is the speed limit, then we can add a force, or add a force to the player to move it that side faster. Add the acceleration to the player. However, if it's not greater than minus 10, we limit it. So let's say it's minus 11. Then we are going to add another force when the player presses left. we're not doing this in the rigid body class, because maybe if we put an explosions rate later or something else, we want to move the player much quicker than its actual velocity. Then we can just update the velocity there. But for now this is pretty okay, and I think for the future as well. We'll have to see. And yeah, now we're just going to do this the same, but for moving to the right. So we're going to check if the velocity is, it should be greater than 10. Let me just think. Yeah, it should be smaller than 10, because minus 10 is, we want velocity to be limited to the absolute value of 10. This means if velocity is negative, it should be greater than minus 10. But for positive values, it's going to switch around. So if you remember from like high school and stuff, if you times by -1 on both sides, you're going to switch around the sign. So let's implement that part. Let's go here. You can just, okay, since this is a one-liner, we can still just leave it like that. It's gonna look better. Okay. So if one of these keys are pressed, I'm just gonna put brackets around this, and the rigid body's velocity x is smaller than 10, then we will add 1. So let's try this, check how it works. So there's a point where it doesn't accelerate anymore. But for skiing as well, because there's no slowdown, there's no friction on this plane. We're just forever moving left and right. This is a frictionless model, you know. We can also change that. So just show here, this is gravity. Now we're also going to add friction. RB, not apply force. New, get 2. Let's just say, okay. So if you want to apply friction, you're going to have to apply it in the opposite direction of the player is currently traveling in. So that means we're going to change the actual velocity. We're going to use the velocity vector. However, I don't want to do it that way. There's another way of doing this to make the actual force smaller, to add like friction. It's called damping. So what you do is you multiply the force or the acceleration with a small, with a like 0.9 to add friction. I will add the effect of friction. It's not the same as actual friction. So what we can say, just look here, force. I think you'll do it like this. Just gonna make it smaller. Let's check if it works. Not working. Why is it not working? Because we're doing it at the wrong place. Order is important. So you can see it's stopping now. This is the damping force. He's jumping a little bit weirdly, and his movement on the X-plane is so quick, it looks like he's sliding around. And that's where you change your actual force you add to the guy. This is actually incorrect by the, sorry, not this one. This one is actually incorrect. Because if you recall from physics, go back to our little board, force applied by gravity is equal to the mass times the gravitational acceleration, g. So we'll fix this so we can add actual mass to our guy by saying RB dot mass times, what's it, gravity. We'll just make this a global variable. This is some nice cleanup we can do. We're just going to put it in the flying fox thing, because this is where we store all the constants. So it's going to be a public static float, public constant static float. Hey, static constant. Let's see. Can't you add both? I mean, come on. Just put it like that. Public. Okay, we'll just do read only. It's fine. Static float gravity. We'll make this equal to like this one. We'll see. We'll change it accordingly if it's not working correctly. Fox gravity. Let's try this. See how it behaves. It is falling like so slowly, you can't believe it. Or are we making it fly? Yeah, we're making it fly. This is not supposed to be negative. Don't make it negative. Don't forget our coordinate system is swapped around. Our y coordinate system. There we go. Okay, that's kind of better. Doesn't really, because it's making a difference, because player's mass is currently 1, so it's just doing nothing. So we'll just add mass in here. Int mass. I mean, you don't even need flag, you can just make it a mass and int. So just initialize this dot mass equal to mass, and go to the player system and give the player his own custom mass. Then we can have a mass for every object we're going to add to the game. So let's just make that 10. Now it's going to have a bit of weight. Let's see. Yeah, see, now he's moving so slowly. Look at him. He doesn't even want to jump. Fly force. Let's make this like RB mass gravity. Just also times this by mass. RB mass. Whee. Yeah, there we go. And now he's moving so slowly in the X direction, it's unbelievable. Now we can just make this greater. It's moving too quickly. I think it's moving. That's a bit hectic. Let's limit that to 5. So this is where you just trial and error what you want to do. And that's pretty good. The moving playable character now. From here on it's much easier because we implemented the physics, the underlying movement physics. And from here you can just like add more objects and the bombs and everything. I mean, we can make this guy explode if we'd like, because we just make him jump very high. We'll just add a giant vector to it. Currently nothing is happening here. So next time when we see each other next time. We're going to add collisions, probably, and bombs. Maybe next time is also going to be 6 months from now. But before we go away, let's just set another variable here, and that's going to be speed, or just speed. So we're just going to say player. And here as well, and hooks put player speed. Now we can just change the variables easier and actually make this, set it somewhere here and just play around with the actual variables. But that is all for today's stream. I really hope you enjoyed it. And here we can also just mark this one as done. We've completed our work. I mean, imagine that. So, see you guys next time. I hope you enjoy your day and keep on the lookout for new videos.